Hi guys, I thought I should catch up with some of these podcasts. So the first one is Atomic Theory and the Periodic Table. Now, I know I've talked about this already, but when you're revising, you might come back and have a look. Here we go. So, we're looking at atoms and their elements. So, as we've discussed, all matter is made of atoms. And we've got a last little atom over there with 3 electrons. What could that be? You should know by now. An element is a substance that's made of only one type of atom. Now, the important other thing that we talked about was the way we derive a name for it, a symbol for it. So this is lithium on our picture here, and we give that the symbol capital L, lowercase I. So the first vowel in the name. Copper, capital C, carbon, capital C, copper, capital C, lowercase u. But there is no U in copper. And of course, 12 in fact of the elements go way back to ancient times, and copper is one of them. So we know that as cuprous, and got that letter, the symbol Cu. But sort of a bit of background knowledge to some of these strange symbols. Wolfram, how do you get T? Tungsten, how do you get W for tungsten? It comes from wolfram. Good work. Okay, so atomic theory. Atoms come from the Greek, or the word atom comes from the Greek atomos, basically meaning unable to divide. And we actually got you guys to do Democritus and Leucippus' little experiment, cutting a piece of paper over and over again. But after them, a couple of thousand BC, we get John Dalton in the 1700s. So there's a big gap between anyone working on the atom, or certainly in the Western tradition. So Dalton proposed that all atoms consist of individual particles. All atoms are called atoms. Maybe meant all matter consists of individual particles called atoms. Atoms of the same element are all alike. Atoms could not be created or destroyed, so Lavoisier would be happy. And atoms combine together in simple ratios to form molecules. Now, all those things still stand. There's nothing wrong with any of that. He didn't have a great deal of understanding of what the atom might have looked like, but his thoughts there are pretty good. Then we have J.J. Thomson proposing the plum pudding model. Let's get myself out of the way there. And you can see here these sort of negative electrons in his pudding. They're the plums in the pudding. So an interesting little variation. Now, so it's back again. Here we go. Get me out of the way. I'll stop doing that. So after that, Ernest Rutherford trying to work out how J.J. Thomson got where he got. William Thomson. J.J. Thomson got his model together. Didn't like it much, so he started playing around with how it might be improved. And he started sending, this is Rutherford here in the picture. He actually used alpha particles to blast a gold foil in this famous experiment. And so here's basically a lead box with a radioactive source in it. Stuff that is called pitch blende. Killed most of them. They'd send that out of. Oh, there we go. They'd allow the electrons. Electrons. What are they? Electrons? The protons. Protons leaving there, aren't they? Alpha particles. To leave this space, and they direct them through this sheet and fire them at something. And so here's your gold foil. Now, of course, if matter was just made of plum puddings, they should all bounce back, shouldn't they? They should all be coming back at you. And so Rutherford didn't expect that. Rutherford expected to see things going through. But he didn't actually expect to see them going all different directions. So we've got stuff going sideways, back and sideways, forward, sideways, and straight through. So there's clearly deflections going on. So his movable screens here pick up all these strange movements. So he started working on a model that had more space in it, so emptiness in it, which led to Bohr creating what's often called the shell model or the planetary model. And he knew that it was inaccurate, but he thought this was at least a good way of representing what was going on. So we've got 2 electrons close into the nucleus made up of protons and neutrons, and then shells of other electrons. In fact, what are these 2 doing floating out here? Maybe they've floated off where they should be. We've got 2 on that shell and 3 on the next shell, which would suggest, this one here says nitrogen. There's no way that's nitrogen, is it? It could be, because there's 7 electrons. So on stuff like that. I wonder if it's just lost its formatting. Interesting. Anyway, so we should have 2 electrons in an innermost shell and 5 Well, I suppose those 5 here are in that second shell, aren't they? In 2 groups. Oh, 2s and 2, 3p, of course they are. So there's that second shell. First 2, inner shell, next 5 in that 2 S and P configuration, which we haven't talked about and I'm not going to talk about now because it's extra stuff you don't need to know about. But these are the valence electrons. These are ones that can be shared or given away in bonding, which we have talked about also. Chadwick sort of kept playing around with this, and he actually discovered neutrons, because one of the problems of the model was that we didn't have any neutrons. We had protons and electrons. But because of the nature of protons, they should have collapsed on themselves, and they had something else to explain the heaviness. And he came up with the idea of neutrons, and also the idea of these s orbitals and p orbitals, which are basically around the nucleus, but using different orbits in their shell groups. We won't go into that because it gets a bit complex for year 9. So we have 3 types of particles: subatomic particles, so they're below the atom level: electrons, protons, and neutrons. The atomic number of an element tells us how many protons it has. So if it, this one's got 6 electrons, which means it would have 6 protons. So 6 protons are in the middle here. These are the blue dots. Because they've got positive charge, they attract 6 negative charges, which otherwise they'll work backwards. And this makes a carbon. Carbon also has 6 neutrons. That's not always the case. We've got 6 little red blobs there as well. So the mass number tells us how many protons and neutrons you're going to find in the inner group. And so we know 3 things about each of these subatomic particles. We know their charge, so electrons are negative, protons are positive, and neutrons are neutral. Whoops, I shouldn't have done that. We know their position. Electrons live around the nucleus in shells of energy. The protons and neutrons live in the nucleus. We talk about protons and neutrons having 1 atomic mass unit. Now, 1 atomic mass unit is equal to 1.66054 times 10 to the negative 24 grams. So I think we call that bugger all in class, didn't we? We also say that electrons have no mass, but they're 1, I forgot the number, 2000 something, of an atomic mass unit. So they're even less than bugger all. But so we just talk about them as having none. Clearly, when you get to a really large atom or a really large molecule, then they're probably contributing some mass when there's lots of them. But generally, their mass is insignificant. So each element has an atomic number. This is the number of protons. The mass number is the number of protons and neutrons. We also have things called isotopes. So they have the same atomic number, therefore they are the same element, but they have different mass numbers because they have more neutrons. So we talk about carbon-12 and carbon-14. The only difference is 2 more neutrons. And of course, all this got arranged into this wonderful thing called the periodic table originally by the wonderful Dmitry Ivanovich Mendeleev. The one we see here in this diagram is actually probably more a Glenn Seaborg or Seaborgian chart. But essentially, it just goes about organising all the known elements into columns and rows of like properties. So this mob here are all highly reactive. They've all got 1 electron in their valence shell and want to lose it. Well, they don't want to lose it, but they're unbalanced with it, and it's a long way from the nucleus, so it's easy to steal. These guys have 2. Over here, these guys have none, so they're not really happy about joining anybody. They're quite happy, all their shells are full. These guys need 1 electron, so obviously group 1A and group 7A are likely to try and bond together. Group 2A, they're happy to group with 6A. And then in the middle we have things that are more likely to make covalent bonds because they're looking at many more. Although some of them will make ionic bonds as well. And we haven't talked about ionic covalent on these slides yet, but we will in a minute. I think that's the last slide. It is indeed. Okay, now so I find the pause button.